All right, so on these, to go back and forth between our derivative and our integral, we're using the fundamental theorem of calculus, which tells us that if we integrate a derivative, it'll take us back to the original, but as far as displacement is concerned, it'll take us back to f of b minus f of a, where we ended up minus where we started. So use the number that you're given and the number that you want to find for your limits of integration. All right, so what I'm going to do is I'm going to say this, that integral, the integral from 1 to 4 of f prime of x dx is equal to f of 4 minus f of 1. Always write that down, be very literal. They happened to already work it for us. They told us it was 17. So this whole thing is 17. So I have 17 equals f of 4, which I'm looking for, minus f of 1, which is 12. So I add 12, and I get f of 4 is 29. And so it's a way to find the original value. All right, on number 2, I'm going to distribute first. They want me to find this. So let's just work this algebra problem right here. This is an algebra problem to solve for this expression. All right, so I'm going to distribute. I'm going to say the integral of 2f of x dx from 2 to 5 plus the integral of 3 dx from 2 to 5 is equal to 17. Now, I'll erase this other. You could rewind if you needed to look at that again, but it might be kind of distracting because mine's all running into each other. But I want to talk about it a little bit. Okay. So why am I doing this distribution when usually you can't distribute? Remember, this really was originally a sigma, and all the sigma rules that we talked about earlier in the year. So this was originally a sigma, and if you had something like 2x plus 1, you could distribute it. And you could factor out like coefficients. Instead of saying 2 times f of x, 2 times f of x, you can just write it out. So here, this is like a German S. So I'm going to say 2f of x dx, because this is just part of the symbol. And then the integral of 3 dx. And they're both going from 2 to 5. So you can just go down the line integrating this and then integrating this. So what I have is right here. It's okay to factor out coefficients because you're just multiplying by it. So I'm looking for this right here. They want me to solve for this. Well, I can work this part. So now I have the integral from 2 to 5, 2 times f of x dx, plus this, the antiderivative of 3 is 3x from 2 to 5, and that equals 17. Just be patient. So I have 2 times the integral from 2 to 5 of f of x dx. This right here is going to give me 15 minus 6. So that whole thing gives me, I'll write it down, 3 times 5 minus 3 times 2 equals 17. So now I have 2 times the integral from 2 to 5 of f of x dx plus 9 equals 17. Keep doing your algebra problem till you've solved for what they want. So now I'm going to keep going. I have 2 times the integral from 2 to 5 of f of x dx equals, I'm going to subtract 9, so I get 8. And then I'm going to divide by 2. So now the integral from 2 to 5 of f of x dx, I actually know its value is 4. So you're working an algebra problem. All right, now moving on to number 3. Just hang in there, you'll get it. You may have wanted to pause that so that you could see the values. See me work it a little more slowly. You can go back through that again. All right, moving on to number 3. Sorry, it keeps getting off the eraser. All right, number 3. On 3A, so it tells us A has an area of 1.5. So I know this area is 1.5, and actually it's under, so I'm going to have to count it. It has absolute value, like this is 1.5. However, when I'm finding the integral of it, I'm going to have to call it negative 1.5. And we know 0 to 6, all in all, is 3.5. And so we can figure out this value because we know negative 1.5 plus some value equal to running total of 3.5. And so this x part here must be 5 because negative 1.5 and 5 leaves you with a total value of 3.5. Remember, when you integrate, it just keeps a running total. All right, so to set this up, though, to actually really show my work, I would say the integral from 0 to 6 of f of x dx is equal to the integral from 0 to 2 of f of x dx plus the integral from 2 to 6 of f of x dx. And then I know 0 to 2, they gave me, is 1.5. It said area of 1.5, but if I take the integral, it keeps a running total, so it's down. So it's negative 1.5 plus the one I'm looking for equals the total, which they gave me is 3.5. So this equals 3.5. And then when you add the 1.5 to the other side, you get the integral from 2 to, 6 of f of x dx equals 5. All right, so let me do that again. That was made a careless mistake with my numbers. But the answer was right. Okay, so what happens is they gave me the area. They said the area of region A, they said the area is 1.5. So all of this right here is 1.5. But when they give me the integral, I have to make it negative because it keeps a running total. All right, so I'm going to split this up from 0 to 6 so I could find 2 to 6. So I'm going to go from 0 to 2 of f of x dx. That's this part. And then I'm going to go from 2 to 6 of f of x dx. And I know the whole thing from 0 to 6 adds up to 3.5. This part I know is negative 1.5 because I can see the picture. This is 2 to 6 of f of x dx is 3.5. So much of this is algebra. So now I know 2 to 6 of f of x dx. If I add the 1.5 over here, I get 5. So the answer to A is 5. Now they want the absolute value from 0 to 6. So if they're talking about the absolute value of f of x, what does absolute value do to positives? This part, it does absolutely nothing. That's still what you get right here, which is 5. And what does it do to this part? It makes it positive 1.5. In fact, the picture would look like this. It would flip this part up and add it to this part. So the integral would add the 1.5 to the 5. So that would be 6.5. Number 4, the graph on the right shows the rate of change, so a derivative, of the quantity of water in a tower in liters per day during the month of April. If the tower has 12,000 liters of water on April 1st, so I know on April 1st, the initial amount, it has 12,000 liters of water. Estimate the amount of water on April 30th. So I need to know A of 30 or W of 30. We'll call it W for water. So what I'm going to do, it says estimate. When they give us these graph paper like this, they actually want us to count the squares to estimate it. So I'm going to take the integral from 1 to 30, April 1 to April 30, of whatever this function is right here. We'll call it the W prime for the rate of water, equals the water at 30 minus the water at 1. All right, now I'm going to estimate this right here. This is the rate of water, and so I'm going to estimate the area under the curve. So, and by the way, look at your units of measure. And some of it is underneath the axis. Let me change colors. Some of it is underneath the axis. All right, so underneath the axis, it looks like I have this square, which I'd say would get lost with this square. They would negate each other. This part would probably negate this part. So now I'm going to add up the rest of the squares that I see, and it did just say estimate the quantity of water in the tower. So this would be, notice it's 6 by 50. So each square, if it's 6 by 50, is worth 300. So this one's 300 right here. This one would give me another 300. This one would give me another 300. And these two kind of go together to maybe give you another 300. So that whole thing, I think, is going to be 1,200. Equals W of 30 minus W of 1, which it originally had 12,000 liters of water in the tower. So I estimate on April 30th, it'll have 12,000 plus 1,200, 12,000 plus 1,200, which would give me 13,200 liters of water in the tank. It should be 500, so I must have counted my squares wrong. It should be 13,500. So this must be 1,500, so I must have missed one. Let's look at it. All right, remember each square, as we're actually, there's so many different ways to find area. So each square is worth 6 by 50, so each square is worth 300. All right, so this is 300, this is 300, this is 300. Oh yeah, so I should have had 5 on them. This is 300, 300, 300, 300, and then together 300. So 300 times 5. Now, why am I not counting these pink ones? Because remember, it keeps a running total. The reason I'm not counting these pink ones is because you actually lose what you gain here. Those cancel each other out. This would be like negative 300 and positive 300. So I'm sorry, that should have been 1,500, and that makes it 13,500. So you actually will learn to count the squares when they give you that. All right, a cup of coffee at 90 degrees. So we know it started at 90 degrees. It's put into a 20-degree room when T is 0. The coffee's temperature is changing at a rate. So here's my derivative. So I'm going to integrate negative 7e to the negative 0.3t dt. I'm going to let it go for 10 minutes. So I'm going to estimate the temperature of the coffee in 10 minutes. So this is the rate the temperature is changing. So if I integrate it, it should take me back to temperature. Temperature of 10 minus temperature of 0. All right, now I'm going to take a second. I'm going to type this function into my calculator and get that value. All right, so I'm saying, I know you can't see it, I'm saying math 9 from 0 to 10. You can do it along with me. I'm saying of negative 7e to the negative 0.3, I'm just using x, dx. So there's so many different ways to find an answer to an integral. You're looking at area, you're looking at squares, you're actually typing into your calculator. There's so many different things we have. This is negative 22.1716. Now what that means is the temperature dropped by that many degrees. When you integrate a derivative, it gives you the total degrees you've lost. So I can estimate T of 10. It started at T of 0 was 90. So I'm going to estimate T of 10 by adding 90 to the other side. So when I add 90 to that, I get 67.828 degrees.